We have now this particular reaction here. This reaction is an overall reaction of two gases given one more gas. This is the overall reaction. This is the experimental reaction that we see. This is the one that we can calculate or can measure the concentrations of the reactants and the concentrations of the products. Now, according to all the data that we collected experimentally, we determined that the rate law, and it's an experimental rate law. Now, we are proposing this mechanism. Okay, so now we have two elementary steps. The first elementary step is given here. The second elementary step is given here. Proposed mechanism is that the first elementary step is fast and it reaches equilibrium. The second elementary step is telling you that it's the slow step. So that means that it has a high activation energy. That means it's going to be the rate determining step. And then that means that this is the one that we have to use in order to write the rate law for my mechanism. And then this one will have to be compatible with the rate law that we have experimentally determined. So let's see how this works. Now, the other thing that I want to mention here is that when we say that it's an equilibrium, really you look at this by this double arrow here. So this double arrow here is telling you that there's two reactions, one going in the forward direction, the other one going in the backwards direction, and they are happening at the same rate. The rate of the reaction going forward, the rate of the reaction going backwards, both of them are going to be happening at the same rate when you have an equilibrium. So this is something very important that we cannot forget. At equilibrium, the rates of reactions going forward and backwards are the same. So let's see. Now we think about the rate determining step. That's the one that it's going to be, that's one that I have to focus on to write the rate law. And that has to be compatible with the experimentally determined rate law. So according to this, and using the molecularity of the reaction, the rate of the second step, which is basically the rate of the reaction because it's the rate determining step, is going to be K times the concentration of NO3 to the power of 1. Remember, in a elementary step, the molecularity is going to be according to the stoichiometric coefficients, times the concentration of NO to the power of 1. Only in elementary steps we can make these stoichiometric coefficients equal to these powers on the rate law. So now this one, we said that we have to compare, and this has to be compatible with the rate that was observed experimentally. So the rate experimentally is going to be equal to K times NO squared times oxygen, concentration of oxygen. They're clearly not the same. They have something in common. They have NO here and NO here, but this is NO3, this is oxygen. So clearly they don't look the same way. So the problem here is that NO3 is an intermediate. So this NO3 is an intermediate, and then because of that, we cannot express the rate in terms of intermediates. Why? Because look at what happens in the overall reaction. Does this reaction has NO3? No, it doesn't. So if it doesn't have NO3, we cannot write the rate of reaction or the rate law in terms of an intermediate. So what is our alternative? Our alternative is that if you look at this step number 1, from step 1, what you have now is that step 1 contains NO3. So what we can do now is find out an expression that relates the reactants with the intermediate to substitute it in the rate determining step expression and see if now we make it compatible. So let's do that. So in this case, from step 1, we already know that R1 is equal to R minus 1, which is the reaction going backwards and forward. And then in terms of the rate laws, R1 is going to be equal to K1 times the concentration of NO times the concentration of O2, and R minus 1 is going to be equal to the rate constant of the process going backwards times the concentration of NO3. Now, if you look at this one, here is the same intermediate that we have here, is that intermediate that we can now substitute to see if we can make something compatible. So now from this one, what we can learn is that the concentration of NO3 can be expressed in terms of the concentrations of the reactants by looking at K1 divided by K minus 1. And then this is going to be NO times the concentration of O2. So now with this one expression here that we have here, now we can substitute it into this one expression here and see what happens. Now, according to this, the rate of the reaction, the rate determining step, is going to be equal to K times the concentration of the intermediate, but that intermediate is actually all this expression in A here. So now what we do is K1 divided by K minus 1, concentration of NO, concentration of O2, times the concentration of NO according to the expression that we got previously. So now you look at this one is a constant, this one is a constant, this one is a constant. So now altogether multiply is going to be a constant. So now the rate of the determining step is going to be equal to a constant times NO, that's going to be NO squared times O2. So now look at the expression that I just wrote here with respect to the one that you got experimentally. It's exactly the same. Now we go from this one, that it's the experimental rate law, to this one, that is the rate that we got for the determining step, and then we see that it's exactly the same. Then we say that this mechanism, it's actually good because it follows all the rules to validate this mechanism. So there's some other examples that you can have, but you can go and practice those.